On this page, we'll look at what's more information about checking conditions for a t-test. In practice, you'll often see the use of a t-test with small samples. Technically, we can use a t-test with small samples only if we know the variable has a normal distribution in the population. But this is hard to verify. Also, no variable has a perfect normal distribution. So what does the requirement that the variable be normally distributed in the population really mean? Because there's no population or sample that gives you a perfect normal distribution. How close to a perfect normal distribution does it have to be? We call a confidence interval or a hypothesis test robust. That's a new word, robust, if the confidence level or p-value does not change very much when the conditions for use of the procedure are not met. T-procedures are robust when the variable is not normally distributed in the population, as long as the distribution is not heavily skewed. This means that we can use the T-model even for small samples less than 30, as long as the distribution of the variable in the population is not heavily skewed. But how can we determine if the distribution of the variable in the population is heavily skewed? In this introductory course, we examine the distribution of the variable in the sample and make an educated guess about the distribution of the variable in the population. So assuming that the sample is a good representation of the population and they will look similar. Now we investigate this question. Can we tell from a sample whether the variability is normally distributed in the population? Well, let's see. Now we'll look at an example where we see variables skewed in the population. Let's start with the skewed distribution in the population. Can we tell that the distribution does not have a normal shape by looking at random samples? The following figure shows the monthly payment on first home mortgages for 5,000 people. That's a lot, right? That's definitely greater than 30, so it should be okay, as reported in the 2000 US Census. Think of this as data from the population of a small town. As you can see in the histogram on the left down here, the variable monthly payments on first home mortgage is heavily right skewed, because you see most of the data on the left and it's kind of tapering down to the right. It's right skewed when we look at the population of all individuals in the town. From this population, we randomly select 20 people. So definitely less than 30, which is our cutoff for, we can use the T model and all that. We did this 3 times. Notice that for each random sample, the shape of the distribution of the monthly payments in the sample is skewed to the right, just like the distribution in the population. In 2 of the 3 samples, we also see outliers, just as we see in the population. So by looking at the sample, we can get a pretty good sense that the variable is not normally distributed in the population. So just looking at these, I can tell that this looks right skewed, at least a little bit. This is just one little sample out of the big population here. This one, it doesn't, I mean, maybe it doesn't look necessarily right skewed. It does look a little right skewed. I don't see any really tall peaks here, but it definitely does not look normal. Remember, normal looks like a bell-shaped curve like this. Maybe some shorter branches of the histogram on the left and the right, but the tallest ones in the middle. And this one looks definitely right skewed as well. You can kind of tell these don't look super normally distributed, I don't think. Oops. Now, in this example, the sample size is less than 30, like we said. The population had 5,000, I think it was, people, but each sample, they said, is only 20 households or 20 people. We can use the t-test only if the variable is normally distributed or at least not heavily skewed in the population. The shape of the distribution in any one of these samples suggests that the variable does have a skewed distribution in the population, so we would not conduct a t-test with any of these samples. A t-test would not be accurate. It's only if it's a normal distribution or fairly normal, or if the samples have at least 30 people or whatever we're testing here. Now let's look at one where the variable is normal in the population. Now we look at a variable that has an approximately normal distribution in the population. Can we tell that this distribution is approximately normal by looking at random samples? The following graph shows the heights in centimeters of 5,000 women. And we've kind of already talked about dimensions on human beings, animals, like height, weight, the length of your foot, just that kind of thing is normally distributed, but we'll pretend we don't know that. Let's see. For 5,000 women, here's the histogram. It looks normally distributed. It kind of has this kind of really tall bell shape. Think of this as data from the population in a small town. You can see in the histogram on the left, the one that we just boxed, that the heights are normally distributed for women in this town. From this population, we randomly select 20 women. So that's the sample size that's less than 30, which, you know, in that case, we couldn't use the t-distribution unless these are normally distributed data. We did this 3 times. So here is the first, second, and third. Notice that for each random sample, the shape of the distribution of the heights in the sample is not skewed, and there are no outliers, it looks like. By looking at the sample, we can get a pretty good sense that the variable is not skewed in the population, which suggests that the variable may be somewhat normally distributed in the population. It's not clear how normal it is by looking at these samples by themselves, but definitely, like I said, definitely not skewed and definitely no outliers that you can tell. Okay. Now in this sample, the sample size is less than 30, just like in the last example. We can only use the t-test if the variable is normally distributed in the population, or at least not heavily skewed. The shape of the distribution in any one of these samples indicates that the variable does not have a skewed distribution in the population. This suggests that the distribution in the population is somewhat normal. Since the t-procedures are robust, like we defined above, we would conduct a t-test with any of these samples. Now, what's the main point that we've said on this page? We previously stated the conditions for use of the t-procedure as follows. 1, if the variable is normally distributed in the population, you can always use the t-procedures. 2, if the variable is not normally distributed in the population, or you cannot determine if it is, the sample size must be greater than 30 for safe use of the t-procedures. We're now loosening these conditions somewhat because the t-procedures are robust, as we defined above. So 3, if the sample is small, less than 30, or less than or equal to 30, let's plot the data like we did in the examples above. If the distribution in the sample is not heavily skewed and does not have any outliers, maybe it doesn't look super normal, but it's not skewed right or skewed left heavily, and there aren't a lot of outliers, then we assume that the variable is somewhat normally distributed in the population and we can use the t-procedures. But if we use a t-procedure for a small sample, less than or equal to 30, it's good practice to include a disclaimer with the conclusion, just to make sure that everybody knows that our results are probably accurate, but they might not be because of these. We might say something like, on the basis of this sample, we are assuming that the variable is distributed without strong skew or extreme outliers in the population. The conclusion from this test is only valid if this assumption is true. Something like that.